Welcome to Compaction of Soils lecture number 4. In the previous lecture, we have studied about factors influencing compaction and also introduced field compaction and compaction equipment, different compaction equipments. In this lecture, we will be understanding about much in depth effect of soil structure on the type of compaction and we will introduce to field compaction equipment and different types of equipment which are available for compacting the soil in the field. The main determinants of the natural man-made deposits, that is the determinants of the nature of man-made deposits are, if you look into it, the soil has to be transported from one place to another place to compact it or to make it into a suitable shape of the structure. So, for that the nature of the soil in the borrow area, it depends upon the grain size, that is the particle gradation, the composition of the particles, and plasticity, the plasticity characteristics, whether it is in the plastic range or whether it is in the highly plastic soil or low plastic soil, or water content, that is the natural moisture content at the borrow area. So, the nature of the soil in the borrow area is governed by three properties. One is the grain size as a particle gradation or plasticity and water content. The transporting arrangement for this for constructing man-made fills basically is also done hydraulically using water in the form of a slurry. This fill construction is called hydraulic fill construction. It is adopted for reclaiming the land in the large areas, for example, over hectares of area to develop the land with a highly compacted soil base. So, for that this hydraulic fill construction is used. The soil is transported with the help of a water in the form of a slurry and then deposited in the desired area, and the water is decanted and the soil, a hardened soil base is ready for the future construction of the at the site. Otherwise, the transporting agent is manually by laborers, human laborers or animals in some sites, and mechanically using the earth moving machinery. Mechanically the soil also is transported from one place to other place. So, this is the how the transporting arrangement is done in the man-made fills. The processing and placement conditions. This is very important for compacting the soil in the field, because the processing and the placement conditions govern the performance of the structure. So, here if you look into this, under 1, the removal of some of the constituents. We have discussed earlier that the presence of the organic matter can influence the structure behavior. So, for that what we do is that some of the organic constituents which may cause the compressibility to the fill and all will be removed, and addition of the other soils. For example, if it is a clay soil and some sandy soil is added to reduce the plasticity, and cement and chemicals. So, some processing in the form is stabilization, which we call stabilization, soil stabilization, where the soils are used as a mixers, or cement stabilization, which is also very popular technique, or some chemicals like lime stabilization is also another popular technique. And another processing and placement conditions are using rolling and compacting devices. This we will be discussing in this lecture. So, determinants of the nature of the man-made deposits are nature of the soil in the borrow area, that is one category, and second one is the transporting arrangement, and third one is the processing and placement conditions. So, in the previous class we have discussed or introduced about the soil structure variation for a particularly a clay type or a fine grained soil, and here in this diagram the unit weight, that is dry unit weight, is plotted on y axis and water content is plotted on the x axis, and 4 different points B, C, D and E. So, if you consider here, we have discussed in the previous class, the soil structure at B is different from soil structure at E. So, here the soil is having less water content, that is WB is the water content B, and at E the water content is WE, which is greater than the water content at B. So, the soil structure what we discussed is that is highly flocculated here and here is in the dispersed nature. And when we go to at maximum dry unit weight and optimum moisture content, we are seeing that the soil structure is undergoes a rotation of the platelet particles and transform that slowly into dispersed structure. That is what we have discussed. We will throw some light into this with the explanation between the attraction and repulsion between the particles, attraction and repulsion between these plate particles, and then we will compare this behavior with coarse grained soils, and then we will try to understand why the coarse grained soils behave different from a fine grained soils. Here if you look into it, as the water content is less, the pore water pressure is predominantly negative. That is, the water or a soil has got a capability or for sucking more water in the form of the pressure here is less than the air pressure. So, what will happen is that the pressure is negative. Under exposed to atmosphere, when air pressure is 0, then the pressure is pore water pressure at this particular point is negative. With the abundant availability of water, the pore water pressure is not so negative, but it cannot be pore water pressure here because we knew that in the compaction conditions the soil can never be reached to saturated conditions. For that case, it is said that the pore water pressure is not so negative by keeping the partially saturated condition for a compacted soil under consideration. So, these points B, C, D and E, these things we will actually form the discussion for us, and where we will see that a change or a transformation of soil structure can be seen. The transformation of soil structure from flocculent or flocculated structure to a more or less a dispersed structure here. So, this transformation can influence the engineering behavior of a compacted soil. Sometimes we have discussed in the previous class like the swelling for a soil compacted at water content B is more than the soil compacted at water content E. So, that is the water content E if the soil can swell less, because already there is an abundant availability of water surrounding these particles, or the full development of the adsorbed water layers have already occurred here. So, what in this diagram has shown that the attraction is very large compared to repulsion here, and as you go the attraction is slightly greater than R, and when you come towards the wet side of the optimum, what you are seeing is that attraction is equal to repulsion. So, it is 50-50 situation, and at the once you cross the reach to the wet side of the farther wet side of the optimum, what you are seeing is that attraction is less than the repulsion. So, mostly the particles will try to repulse. So, whatever the energy you are giving, it is actually going to in the form of a futile bumping of the soil at that particular point. So, we will try to look the structure of the soil compacted by kneading as a function of the water content at compaction. So, if you look into it, the reason for an inverted V-shaped curve. So, we said that the reason for an inverted V-shaped curve for fine grained soils can be explained in the terms of soil structure by T.W. Lambe 1958. After Lambe 1958, the reason for a V-shaped curve, inverted V-shaped curve for a compaction, for a fine compaction curve for fine grained soils can be explained with the basis of the soil structure after Lambe 1958. So, as you all know, the clay mineral particles, which are a major constituent of fine grained soils. So, clay minerals are the major constituent of fine grained soils, have a net negative electric charge on them. The reasons are discussed in the previous lectures. The face of these particles are negatively charged, whereas the ends are positively charged. Because of the breakage or the breakage of the bonds, the ends of the particles are positively charged and all the faces are electrically negatively charged. So, this causes attraction and repulsion depending upon the availability of the water in the soil. So, once you look into it at point B, that is, let us draw the same diagram over here for ready reference. Gamma D water content, the compaction curve, this is 0 air voids line, So, let us indicate point B, let us indicate point E, D, C, so at this point the water content is WB, at this point water content is E, at this point the water content is WD, which is equivalent to optimum moisture content, and this is nothing but gamma D max, maximum dry unit weight. So, let us try to discuss one by one about the difference in engineering behavior between point B and point E, and how this inverted V shape is explained by Lambe 1958. So, let us look into this slide. At B, when a small amount of water is added, say to achieve water content B, there are not enough water molecules to neutralize the charge on the surface of the particles. That means, at point B, when a small amount of water is added, say to achieve water content B, there are not enough water molecules to neutralize the charge on the surface of the particles, and the adsorbed water layer is said to be depressed. So, the adsorbed water layer is said to be depressed. When compaction stresses bring particles together, particles align themselves with a very open arrangement of particles with very strong contacts. So, with this arrangement, what will happen is that at this point the soil structure is something like face to edge orientation. You will see that very open arrangement of the structure is possible, something like truss like arrangement is possible with a flocculated structure. Flocculated structure with face to edge or face to face orientations to some extent. Basically the structure is a open arrangement, something like a truss like connections. So, each joint actually has got sufficient connection strength to restrain or to support the load. So, at this point, when a point B, basically we are discussing at this, for this point B, when a small amount of water is added, there are not enough water molecules to neutralize the charge on the surface particles. Still there is some negative charges are prevalent, and with that what is happening is that there is some attraction which is taking place, and the adsorbed layer is said to be dispersed in nature. So, with that what happens is that when compaction stresses bring particles together, they align themselves with a very open arrangement of particles with very strong contacts. The contacts between these particles is very strong here. With attraction is much more than repulsion. With attraction much more than repulsion, so the structure is what we are naming it as a flocculated structure. So, this implies to this type of structure with the open arrangement, truss like connections. The analogous to this explanation is given like a truss like connections with very strong contacts. So, this is at this point. Now, when you progress along this curve, if you add a little amount of water, that is more than WB, then the water content C, then now you are supplying more amount of water to the soil. So, there is a certain development of adsorbed waters and a decreasing in the tendency of this connections between the particles, and there is a decrease in the tendency of the neutralization, where what will happen is that the attraction is just still more than repulsion, but still the structure has not transformed into a dispersed structure, but what still it remains is that with an increase in water content, that is WC greater than WB, that is WC is the water content at point C, and then this is the density corresponding to that point. So, WC greater than WB at point C, with an increase in water content, the adsorbed water layer is not so depressed. With an increase in water content, Wc greater than Wb, the adsorbed water layer is not so depressed. The particle forces would still be negatively charged, that is what we are discussing. The particle forces are still would be negatively charged, but not as much they were at Wb. So, this the negative charges because is decreasing because there is an abundant availability of water, because of the water content at point C is more than the water content at B. So, upon being subjected to compaction stresses, because same soil with is subjected to compaction stresses, most particles get aligned in a phase to phase configuration. So, mostly now there is a tendency of switching the particles from phase to phase configuration, but some get pushed into a phase to edge arrangement, some get pushed into a phase to edge arrangement. The resulting structure is still flocculated, but with weak particle to particle contacts. So, if you ask this the soil compacted at water content B has got more open arrangement and more resistance for the strength than the soil compacted at water content Wc. So, the resulting structure is still flocculated, but with weak particle to particle contacts. This is one thing which is important to be noted. Now, let us go to point D, that is nothing but maximum dry unit weight and optimum moisture content. At point D, upon the addition of at larger quantities of water, that is here what we did is that we started increasing gradually water and reached the peak. So, this point is said to be the optimum moisture content for this soil, and the vertical ordinate here is the dry unit weight, which is nothing but gamma d max, that is maximum dry unit weight. So, with this, upon the addition of at larger quantities of water, the trend described above continues to operate. The same trend tries to operate, and compacted soil of higher and higher unit weight with structures which are less and less flocculated is obtained. Now, the structure is undergoing a transformation from flocculated to dispersed until the water added produced optimum water content. So, at point D, upon the addition of at larger quantities of water, the trend described above continues to operate, and the compacted soil of higher and higher unit weight with structures which are less and less flocculated is obtained until the water added produced optimum water content. So, here the why this happens, all these things we have discussed in the principles of compaction, but at point D, upon the addition of at larger quantities of water, the trend described above continues to operate, and compacted soil of higher and higher unit weight with structures which are less and less flocculated is obtained until the water added produced optimum water content Wd. Now, let us try to migrate to the wet side of the optimum, that is at point E. So, at point E, that is at water contents above optimum, the adsorbed water layers surrounding the particles are well developed, and most of the electrical charges and clay particles is neutralized. Most of the electrical particles is neutralized. So, at water contents above optimum, that is at point E, that is water content is corresponding to this point is We is greater than all these water contents. So, at water contents above optimum, the adsorbed water layers surrounding the particles are well developed, and most of the electrical charges and clay particles is neutralized. That is, now the neutralization of the clay particles has occurred, and during compaction process, these well developed adsorbed water layers surrounding clay particles interfere with each other and prevent particles from coming close to each other. So, during the compaction, what will happen is that these mostly these well developed adsorbed water layers surrounding the clay particles, they interact with each other and they hinder the particles from the coming close together, because the adsorbed water layers are now completely developed. With that, what will happen is that during the compaction process, these well developed adsorbed water layers surrounding the clay particles interfere with each other and prevent particles from coming close together. So, the energy supplied gets dissipated in futile bumping. That means that what will happen in the compaction test, if you observe in the laboratory compaction test, if this is the mold under consideration. suppose this is the layer undergoing compaction. At this particularly at wet side of the optimum, if the hammer energy is supplied, then soil undergoes a typical failure where it is also called a heaving failure will occur surrounding the area where the energy is supplied to the compacted soil. This is in the compacted mold. At wet side of optimum. And soil appears to be something like water oozing out of the soil, or it is also called the bleeding of the soil. So, during this compaction process, what will happen before this energy is transferred, that means that without transferring this energy to the particles to make it into arrange into dense positions, what will happen is that the soil fails, and in the process the energy gets dissipated in futile bumping. So, this is actually a typical bumping which is shown here with failures like this. During compaction process, these well developed adsorbed water layers surround the clay particles, interfere with each other and prevent particles from coming close to each other. So, this is a case which can happen in on the farther wet side of the optimum. That is the reason why very difficult for compacting clay soils on the wetter side of the optimum. So, this is a typical resulting dispersal structure which is shown here. So, resulting dispersal structure at this point is shown here. So, what we have discussed in this particular example is that how the soil structure is transforming as we are proceeding on the from the left hand side, that is on the dry side of the optimum to the wet side of the optimum. Now, the influence of soil structure on the type of the compaction. This is also like suppose if you have got static compaction or impact compaction or kneading compaction. These are the three different types of compaction we have introduced in the previous lecture. But if you see for this in this table, a static compaction can produce a water content at water contents like dry side of the optimum, that is this side is called the dry side of the optimum, dry side of the optimum. And this is called optimum, that is wet side of the optimum on this side and dry side of the optimum is on the left hand side. So, here the static compaction does not influence much the soil structure remains flocculated. That means that the whatever the energy which is created to static compaction remains something like a flocculated structure is flocculated both on the dry side of the optimum and wet side of the optimum. Impact compaction to some extent produces flocculated to dispersed structure on the wet side of the optimum. On the dry side of the optimum, it remains something like a flocculated structure on the dry side of the optimum. Kneading compaction, if you adopt a kneading compaction and that produces something called a flocculated structure on the dry side of the optimum and a dispersed structure on the wet side of the optimum. So, the type of the compaction like static, impact and kneading, where the dry of OMC produces mostly a flocculated structures or open arrangement or a truss like arrangements, and the wet of OMC flocculated or flocculated dispersed for impact type of compaction and dispersed for kneading compaction. So, this actually is to be decided for the depending upon the type of the structure under consideration. Suppose if it is a load bearing structure, something like a highway embankment or railway embankment, where the soil is compacted on the dry side of the optimum. Suppose if it is some earth dam or a compacted clay liner for a landfill, then it is compacted on the wet side of the optimum to have the sealing efficiency. So, influence of compaction conditions on soil structure, we can summarize. The soil structure becomes more dispersed. soil structure becomes more dispersed as the placement water content is increased. So, if you are on an average, if the water content is increased, the placement water content is increased, the soil structure tends to change to disperse. The amount of compaction is increased. As the amount of compaction is increased, that is also we have seen that it also shifts to the left hand side of the right side of the optimum, where the more air is removed quickly. With that, the amount of if you increase the amount of compaction, then also the soil structure becomes tries to transform towards a dispersed nature. By using a type of compaction which introduces more shearing action in soil during compaction process. Suppose if you use a type of compaction which induces more shearing action, then that also can change the soil structure from flocculent to dispersed nature. Soil compacted at water content of OMC would be more dispersed. So, soil compacted at a water content the soil compacted at a water content greater than OMC would be more or less a dispersed structure. Soil compacted at a water content more than OMC would be more dispersed. So, having seen this, now let us look the engineering behavior of as a function of density and structure. So, we have seen that how the soil structure changes from the dry side of optimum to wet side of optimum. Now, what we should try to do is that to link this behavior to the engineering behavior like swelling, shrinkage of a soil, and permeability, that is the capacity to drain the water, and strength, basically how the stress strain properties change for a given soil, and compressibility of a given soil. So, let us try to select swelling. When the samples of soil from B and E are given access to water, which would swell more? That is the question we have already asked before. So, if you ask if the soil sample is compacted at a water content B and water content E, where water content B is on the dry side of the optimum and water content E is on the wet side of the optimum, then which soil would swell more? So, the answer is that the soil at B swells more, because the soil at B has a greater thirst for water and swells more, and also charges are not neutralized. So, the tendency here is has got a more affinity for water attraction. So, with that what happens is that the soil which is compacted on the dry side of optimum swells more. That is, soil compacted at say at point B swells more rather than the soil compacted at water content E. Then when you come to second parameter, that is shrinkage. Upon drying, soil at B will begin bodily to interfere with each other, because at soil at B has got a open arrangement like a flocculated net like arrangement, pack of cards like arrangement, where they derive high connection strengths. With that what happens is that soil at B as a bodily try to interfere with each other and will not allow the soil to shrink. So, the shrinkage of soil at B is less than the shrinkage of soil at E. So, whereas the soil at E will approach each other without hindrance as the soil is dried, hence high shrinkage. So, the reason here is explained here is that upon drying, soil at B will begin bodily to interfere with each other and will not allow the soil to shrink, whereas the soil at E will approach each other without hindrance as the soil is dried, and hence the high shrinkage. So, the soil at this point is high shrinkage, and then where the soil at this point is having a low shrinkage. So, high swelling and low shrinkage, low swelling and high shrinkage. These are the contrasting phenomena which one should note here. And the second one is that another parameter which we have forgotten is the construction pore water pressures. Higher the magnitude of pore water pressure are reached with soil at E than the soil at B, since at B the soil is still drier and has initially more relative pore water pressure. So, the more negative or pore water pressure, the construction pore water pressures first they will try to neutralize and then try to increase above that. So, with that what will happen is that has more rigid structure. So, higher magnitude of pore water pressure are reached at soil E at point E than with soil at B, since at B the soil is drier and has initially negative pore water pressure and has more rigid structure. So, the construction pore water pressures are more at point E than rather than at point B. The second point, very important point, is the permeability. The soil at B will exhibit the same permeability in all directions, whereas soil at E will be more permeable along the particle orientation than across the particle orientation. So, let us try to look this. So, what we said is that let us assume that a open arrangement like a truss like arrangement which is shown here. So, soil at point B, soil at point E with flocculated structure, dispersal structure. Now, we are seeing permeability. Soil at B will exhibit the same permeability in all directions. So, the permeability is, suppose if I put this as x and y, the soil at B, the point B, that is at this point, soil at B has got identical permeability in both x and y directions. Similarly, that soil at E is perpendicular to its plane of this platelet particles, the permeability is less. Along the plane of the particles, the permeability is very high. That means that water cannot flow through this easily, but water can flow along the particles. So, in this direction Kx is greater than Ky. So, that is one thing with the dispersal structure. What we are trying to see from this slide, soil at B will exhibit the same permeability in all directions. That is, here at flocculated structure, soil exhibits identical permeability both in x direction and y direction. In this case, perpendicular to this plane, that is the permeability is less compared to across the particle orientation. So, that is one important consideration from the engineering behavior point of view should be noted. Now, coming to the compressibility. Compressibility at low applied stresses, the dispersed soil will undergo sizable volume change, whereas the flocculated soil would be less compressible on account of the truss-like arrangement of the particles with strong contacts. So, the compressibility, if you compare at low normal stresses or low stresses, applied stresses, the dispersed soil will undergo sizable volume change, whereas the flocculated soil will be less compressible on account of truss-like arrangement of particles with strong contacts. So, if you consider again the point B and point E, the soil at point B would undergo less compressibility compared to soil at point E. So, the soil at point E will undergo a sizable volume change at low applied stresses, whereas soil at B will undergo less compressibility, less compression because of a truss-like arrangement of the particles at this point. That is, this is attributed to a flocculated structure which is prevalent here and which is because of the strong particle contacts. At some limiting stress, the truss-like arrangement would collapse and the soil would exhibit high compressibility in relation to dispersed soil. So, as the stresses are increasing, applied stresses are increasing, the soil what will happen is that this whatever the existing the prevailing the truss like arrangement, they collapse and they change into a dispersed structure. At high applied stresses, the initially flocculated and the initially dispersed would have similar structures and would exhibit similar compressibility. So, at low applied stresses, the soil at point B exhibits less compressibility compared to soil at point E, that is on the wet side of the optimum. At some limiting stress, what will happen is that these truss like arrangements collapse and they switch over to a dispersed arrangement. But at very high applied stresses, both the soil which is initially flocculated as well as the initially dispersed will have the same structure. So, they will exhibit the same compressibility. So, this is very important point which should be noted and which will be carried out for understanding the consolidation behavior of soils. The next one is the stress strain behavior of the soil, because now what we are trying to do is that we are playing with the compaction curve and we have selected 4 points B, C, D and E, and where B and C are on the dry side of the optimum, where E is on the wet side of the optimum and D is at the optimum. So, at this particularly with reference to stress strain, upon application of the stress, the soil at E will deform steadily, whereas the soil at B with its truss like arrangement will resist deformation, and the stress strain curve would rise to peak and drop down when the flocculated structure suffers a collapse. So, if you consider a stress strain behavior of a soil compacted with water content B and water content E. So, let us try to compare in elementary terms, but this will be introduced in the while discussing shear strength, but let us give a preliminary idea about this stress strain behavior of the soil. So, if you see here what it is being told is, say if you put stress on the y axis, strain on the x axis, the dispersed structure will increase steadily. That is what is upon the application of the stress, the soil at E will deform steadily, whereas the soil at B with its truss like arrangement will resist deformation and the stress strain curve would rise to peak and drop down with when the flocculated structure suffers a collapse. So, what is being told is that so this is for soil at water content B, which is on the dry side of the optimum. At WE, which is on the wet side of the optimum. So, what is two distinctive behaviors are seen as with reference to stress strain behavior for a flocculated structure as well as dispersed structure. If you see here, for a flocculated structure, the soil is able to support, or the modulus is also very high. Initially the modulus is very high and it reaches a peak. So, at this point what will happen is that the structure starts, or these truss like connections start collapsing. So, in the process what will happen, slowly the structure again transform to a dispersed structure again. So, here the brokage or a breakage of bonds or a strong contacts which are there, particles is there, it starts here. So, till that point the soil is able to generate or a peak strength, then the structure starts breaking and then changes out to this particular point where the dispersed structure prevails here. So, at high strains, soil samples from B and E will have essentially the same particle arrangement and will thus exhibit about the same strength. So, here the soil structure is same, similar to compressibility, but high applied stresses, we said that because both the soils have got the same structure, so they exhibit the same strength. Similarly, here at this particular point, all these truss like connection particles which are there earlier are broken and reduced into a dispersed arrangement. So, with this what will happen is that the structure is now exhibiting, the soil is exhibiting now the same strength with higher strains. So, that is very important parameter which should be noted for explaining the stress strain behavior of the soil, which will be discussed in length during the shear strength of a soil. So, let us, having seen this effect of soil structure and then the type of the compaction, let us try to again compare the distinctive behavior between a compaction of the coarse grained soils and cohesive soils, that is fine grained soils. And we said that coarse grained soils initially they experience a reduction in the dry unit weight, and then after increasing water content, the films which are surrounding the particles or grains will disappear, and slowly they will allow the particles to come closer. So, produce a maximum dry unit weight. So, and contrary to this, the fine grained soil has got an inverted V shaped curve, and that is where the variation in the density is very high for a fine grained soil when compared to a coarse grained soil. So, let us look into this. Upon compaction, the behavior of the clean sands or a clean coarse grained soils having fines less than 10%, that is silts and clays less than 10%. The different from the fine grained soil on account of two reasons. The reasons are sand grains are more or less equidimensional and not plate like particles. That all we know, that the sand grains are more or less equidimensional and not like plate like particles in a fine grained soil, and they are electrically neutral. When you compare the charges, the sand grains or the quartz grains have got electrically neutral status on the surface, whereas compared to the platelet particles, they are completely neutrally charged. So, they are bound to change depending upon the availability of water. So, let us look into the distinctive behavior by comparing with these two diagrams, compacting coarse grained soils, where you can see a typical a compaction curve is drawn here. So, this is the dry unit weight at point A, and at point B soil exhibits a decrease in the dry unit weight, and upon adding water the water content increases, and closer to saturation it reaches the maximum dry unit weight. But if you see, the typical variation in the dry unit weight is very less for if with increase in water content for a coarse grained soil, a clean coarse grained soil having fines less than 10%, and this is the zero air voids line whatever you are tracking, and this is the compaction curve for a fine grained soil. So, total variation of the dry unit weight sand compacted at different water contents is small compared to the variation possible in the fine grained soil. That is what actually is being discussed here. Total variation in dry unit weight and dry unit weight of the sand compacted at different water contents is small compared to the variation possible in fine grained soils. So, this is what we explained in the previous class is that, so these are the solid grain, uniform grain particles which are surrounded by water particles which are there here, and with that what will happen is that because of these capillary tensions developed with the water films which are surrounding the particles, and they create something like an apparent cohesion, and because of that the soil exhibits low density or low unit weight, and upon adding water these films get washed, and then they allow the particles to come closer. That is the reason why you are seeing that the degree of tendency of the capillarity effect decreases, and then you will see an increase in the density. So, having seen a distinctive behavior, now it is time for us to introduce again the compaction equipment or a compaction plant, and we said that different types of rollers are used, because now we have seen the distinctive behavior between a coarse grained soils and fine grained soils. So, we are required to understand about which type of equipment is useful for rollers, which type of equipment is useful for compacting the soil in the field. So, they are predominantly, like in the last class we have introduced, they are rollers or rammers and vibrators. So, depending upon the soil classification and soil type, so whatever we have learnt in the previous class, once we have got a soil classification or a soil group from the particular borrow area, then based on that the typical type of equipment has to be selected to compact the soil in the field for a given structure, and also depending upon the function or the end serviceability requirement. Suppose if it is for a highway embankment, it is the placement water content has to be decided, and different types of rollers have to be used. So, now let us look into different types of compaction equipment which are available for compacting the soil. So, compaction mechanisms, what we said is that kneading mechanism, tamping mechanism, vibration and impact type. So, vibration is basically we have discussed that is used for coarse grain soils. Kneading and tamping to some extent is used for fine grained soils, sometimes impact compaction. So, compaction mechanisms as you see here in this particular chart, compactor zones of application and compactive efforts. For clay soils, a type of roller called a sheep's foot roller, that is basically used here, a sheep's foot roller, and for 100% sand or a clean sand, the compaction equipment changes here almost to the vibratory type. Say rocky type soils in the rock filled dams and all, the rock tamping the grid roller has to be used. So, here sheep's foot roller is used primarily for cohesive soils or a fine grained soils which are having more fines. Tamping foot roller, that is high speed tamping foot roller. So, as the clay transforms from 100% clay to 100% sand, you can see the variation in the type of rollers or type of compaction equipment used in the field. High speed tamping foot roller, towed tamping foot roller, heavy pneumatic roller, multi-tired pneumatic roller, smooth steel drums roller and vibratory rollers, and grid rollers basically for a rocky type strata. So, the compactive effort, if you look into it, static, kneading and impact vibration, that is here, and static weight and kneading and impact vibration. Sometimes the static weight will not help. So, with this the vibration, which is actually static weight as well as vibration, is required to apply for compacting the coarse grain soils. So, if you see that is what we have discussed, cohesionless soils can be compacted by kneading, tamping and vibrating, and cohesive soils by kneading, tamping and impact vibration. So, compaction of the cohesionless soil materials are compacted by vibration, and static load produces a very little compaction of the loose sand. We have seen this through a demonstration test, and medium and fine sands do not compact easily when moist because of the shear strength developed by the capillary forces. That is what we have discussed, because these films will not be allow the particles to come closer. Because of that, medium and fine sands do not compact easily when moist because of the shear strength developed by capillary forces. And dry or submerged sands can be compacted by vibration. So, a dry sand or a submerged sand can be compacted. Submerged sand means completely the sand saturated with water, can be compacted by a vibration technique. And clays cannot be compacted by vibration. That is one thing. We have also seen that by performing a simple experiment in this in the previous lecture, we have demonstrated that clays cannot be compacted by shaking, where the sand can be made to rearrange into new positions. So, small amount of pressure is required to force the grains of clays with high water contents. So, if you take the soil with very high water content, a small amount of pressure itself is sufficient to push the particles closer. The free water surrounds the particles and low viscosity. That is also one thing, is that the free water which is actually surround the particles and the low viscosity, and high degree of compaction cannot be achieved because of the thick layer of water surrounding the particles. So, that is high degree of compaction cannot be achieved because a thick layer of the fully developed absorbed water layer, which actually will prevent the particles from coming closer. That is also another influence which actually inhibits the compaction. So, types of the rollers, if you look into it, there are the smooth wheeled rollers, vibratory rollers, pneumatic tire rollers, sheep's foot rollers. So, smooth wheeled rollers or vibratory rollers or pneumatic tire rollers, and sheep's foot rollers, if you look into it, basically the rammers are dropping weight, including the piling equipment, internal combustion type and pneumatic type. These are the different rammers which are used in the compaction field. And what we are seeing here in this picture, a smooth wheeled roller with a rubber tiled roller with 80% coverage area, which can actually induce 700 kilopascals pressure. So, with 80% coverage area up to can induce around 700 kilopascals. So, 100% coverage area under wheel load with the ground contact pressures up to 380 kilopascals. That is basically a general specifications for a smooth wheel roller, but here which is shown here a picture which is shown a rubber tiled roller with 80% cover area which can exert ground pressures up to 700 kilopascals and suited for firm cohesive and well graded granular fills. Except the rocky types, a well graded granular piles can be, and due to this particularly this multi-tiered roller cannot compact, or a smooth wheel roller cannot compact a uniformly graded sands because of the roller pushing into the soil. Because of this, what will happen is that this is unstable in uniform stands due to roller pushing into the soil. So, 100% coverage area under wheel load with ground pressures up to 380 kilopascals and suited for firm to cohesive and well graded granular fills. So, except rocky type soils, this is used. So, conventional smooth wheel rollers have 18 tons is the, and another tandem rollers are 1 to 14 tons. 3 axle tandem rollers is the 12 to 18 tons. This is the conventional weight, and weight can be increased by ballasting the rollers with water or by heavy sliding weight. So, by ballasting with water or by with the sand, then the weight can be increased, and performance is affected by the load per inch width under compaction rolls and the width and diameter of the rolls. So, this is about the smooth wheel rollers, and another point, the third point is that load per inch width and diameter control the pressure in the surface layer of soil. Dimension of the rolls affect the rate with which the pressure decreases with the depth, and suitable for gravels, sands, hard core crushed rock and any material where crushing action is needed. So, the smooth wheel rollers are suitable for gravels and sandy soils and hard core crushed rock where some certain extent of crushing is required, then this technique will become handy. And the moisture content should be adjusted to the optimum moisture content, and depth of the layer compacted is that subgrade is around 150 mm and base of the embankment is around 450 mm. So, this is about the smooth wheel rollers. There are also another rollers like pneumatic type rollers and sheep's foot rollers. So, in the next class we will be discussing about this the relevant equipment for sheep's foot rollers and their applications for different type of soils, and then we will try to solve 1 or 2 problems pertaining to the compaction. With that, actually we will be able to see how a soil which is compacted in the field can be compared with the laboratory and assess the relative compaction characteristics of a soil, because this is very important for us to assess the field compaction and compare with the laboratory compaction. So, we define the term called relative compaction, and based on that we will try to define a criteria and discuss about the specifications required for field compaction.